So we're going to start talking about. I'm going to sort of do a speed run through a few of the chapters of the book. This is what we're going to start with. We're going to start with algebra in the Renaissance. So, as during the Middle Ages, as more and more complicated commerce was happening, it wasn't just a matter of like bartering or my selling something to you and you giving me money and this sort of thing, but there really started to become very complicated commerce things, commercial activities going on. And so one of the things that we're not going to talk about at all is the invention of double entry bookkeeping. The method of accounting that we use now that sort of accounts for things in terms of debits and credits, and without having some sort of accounting system like that, really the economy that we have today would not be possible, just because it's difficult to keep track of various different things, spending money to buy stuff over here as part of a venture, to sell it in that part of the business and this part of the business over here, and how those things relate and how all this other stuff relates. You really need a more robust accounting system. So, for example, they were still using Roman numerals, and it was a while until they started using kind of the numerical system that we use now. And there's a number of reasons for this. Just a lot of it, I think, just had to do with not wanting to change. And as I think our book points out, our modern custom today of actually writing out the amount of money on a check, to the extent that people still write checks, comes from this idea here, that you want to have more explicit things rather than just writing things out in a decimal expansion or something like that. Anyways, so the monetary economy started to emerge. It was less barter. It was more based on money, and so double entry bookkeeping, but also more sophisticated mathematics had to sort of be invented to solve the problems that they were being faced. And you can look through the book at some of the different types of motivations for the problems that they were looking at. But one of the things that happened is a new professional branch of mathematicians began to emerge. And so that's kind of one of the things that we're going to concentrate on here. So this gives us algebra in the Renaissance. So one of the main things that we're going to focus on is going to be solutions of polynomial equations. And we're really going to look mostly at cubic equations for this chapter. And there's a reason for that, and we'll get to that in just a moment. Excuse me. So one of the main things that happens here is that if you look at the algebra problems that we were looking at so far, I wrote them symbolically. But remember, if you read them in the book, they were all described. The problems themselves were described like as a word problem, okay? And then the solutions were also, described as word problems, or described as like a procedure. First, take the quantity and add 5 to it, or whatever. This type of thing that we've covered in previous weeks in this class. We started getting a move toward symbols. Now, it's not the symbols that we use today. It's basically using just letters. They use letters like P for plus, for example, things like that to mean, plus. Well, I don't know. Sorry, out of the corner of my eye, I saw something pop up on my phone and it confused me for a little bit. Anyways, so they use different symbols than we use now, but they were still starting to use symbols, which was a big sort of an advance. We've talked about that before. It's a big advance to get to what we have now. So one of the interesting things about this time is that mathematicians, instead of discovering something and kind of publishing it right away to sort of ensure priority, like I was the first one to do this. For example, if you look on the archive, it has the timestamp there, so you can actually say I was the first one. You published it the same day as I did. We posted it the same day, but I posted it earlier, so it's my discovery to the extent that it happens. Anyways, that's more of a joke. But the point is, nowadays, mathematicians want to publish their results for a number of reasons. Some of it is to encourage, it's because they want to, say, sort of stake their claim and say it's my result, but also because they want to sort of share what they've done so other people can sort of take it and go from there. At the time that we're talking about, which is going to be like the 14 and 1500s, going on into the 1600s, it was a little bit different. And so if you had a position as a university professor that you wanted to keep, the way that you kept that is by ensuring that nobody else was better than you. So what does that mean? You could publicly challenge other math professors to be like, I'm going to give you a list of problems to solve, and you give me a list of problems to solve, and then if whoever solves the most of the other person's problems gets to have the professor's gets to have the professor job. I can't remember which YouTube channel I watched that did this. I don't watch a lot of YouTube channels, so it's probably, I think it's Veritasium. There was recently, I think, a video about this idea in the last year. I think he did a video about this in the last year, about this sort of professor dueling. So here's what happens. People are studying the cubic equation. A lot of things happen. I'm going to show you kind of in the context of the cubic equation, something that happens. People are studying the cubic equation. This is the general cubic equation, ax cubed plus bx squared plus cx plus d is equal to 0. And what they're able to do, let's see if I can point here correctly, they're able to reduce it to this, all cubic equations, to this called depressed. It's called the depressed. Here it's called reduced form. Another name for it is the depressed cubic equation. So the idea here is that if you can solve this depressed cubic equation, since all cubic equations can be reduced to this, which I'll explain in just a moment, then you can solve all cubic equations. So this, solving this type of equation is kind of the key here. Now, one thing that is different about how they approach things, sort of different, not just in the sense of different notation, but just the way that they approach things, they only allowed positive coefficients in their equation. So if we have something like this, let's see if I can point to it. If we have something like this, which is x cubed plus px plus cubed is equal to 0, this is not the same equation as x cubed plus px is equal to q. Now, of course, they're not the same equation because the q here should be minus q of the one there. Okay, but like in their minds, these are two different types of equations because we always have to have positive coefficients. Okay, so then there's different ways depending on whether you have the p and q over here or over there. There's basically 4 different types of depressed cubic equations. Okay, and so if you want to study all of the depressed cubic equations, there's these 4 different equations that you have to solve. Okay, so the change of variables that you make is to say, well, actually, let me do this. So if I take this, if I take the general cubic ax cubed plus bx squared plus cx plus d, and I'm going to do something that they didn't know how to do, but we know how to do now. They know how to find the answer to what I'm about to find, but not the way that we're doing. If we take the second derivative of this, we get 6ax plus 2b. And if we set this equal to 0, we're going to get an inflection point. And what we do is we see that the inflection point is equal to minus b over 3a. And so what we do is we say that t is equal to x minus b over 3a. And so essentially what we're doing is we are sort of centering the cubic function at the inflection point. If you take this change of variables, I'm sorry, I got this backwards. That would not shift it the right way. So we say this, x is equal to t minus b over 3a. So t is equal to x plus that. In other words, in t, it's like it's shifted over to be centered at the inflection point of this polynomial. Okay, but what I'm saying is if you take this and plug it in here, it will reduce it to an equation of this form. Actually, a reduced equation of this form, a depressed equation of this form with all of the coefficients on the left-hand side. So again, one more time, if you take this and plug it into here, you're going to get a depressed cubic equation of the form t cubed plus pt plus q is equal to 0. And if you actually do it, you'll see what the values of p and q are in terms of a, b, c, and d. Okay, so then again, that's just an exercise that you can do. But the point here is that if we can solve equations like this, if we can solve cubic equations like this, then we can solve cubic equations like that. And then also, you have to do the thing here where you put all of the coefficients on different sides and stuff like that. Okay. But this is very challenging stuff. I mean, I think if we try to solve a cubic equation nowadays, we just give up. The thing that we want to do when we try to solve a cubic equation is hope that we can find a root and then, factor that out, do polynomial log division, and then we have a quadratic. So really what we like to do is reduce things to quadratics. That's not always easy to find that first root, though. In fact, most of the times it's not possible, at least sort of to do it in an analytic way. Not that there isn't a formula, I just mean by inspection it's difficult to find the root. Okay, so now what we're going to look at is we're going to look at this mathematician. You know what? I'm going to guess his name is Scipione. Oh man, I should have looked this up. Now I'm a little bit embarrassed. Scipione del Ferro, and I hope he is not offended that I'm not saying his name correctly. Anyways, so he was the first one to solve this depressed cubic equation. And notice he did solve it in this form here, the x cubed plus px equals q form, not the x cubed plus px plus q equals 0 form. So again, we're thinking about these as two conceptually different equations. X cubed plus px equals q is conceptually different than ax plus pq minus q, or sorry, ax plus px minus q is equal to 0, because again, we always want to have positive coefficients. Okay, so again, what he did, so the time that he lived, so let me tell you the time that he lived. He was alive from 1465 to 1526. So what he does is he finds a solution, like I said, to the depressed cubic equation, and like everybody at the time, he kept it silent. He kept it hidden, he kept it hidden, he kept it hidden. Eventually, in 1526, he dies. But before that, he tells his students the method. So two of the students he tells that will come back in just a moment here, at least once each. Fiore and Delanave. Okay, so he tells both of his students this right here, and these guys were both alive in the first half of the 1500s, from like 1500 to 1550. I think his death was something like 1500 to 1501, and I couldn't find information about him. So what happens again? Del Ferro knows how to solve the depressed cubic equation, but he doesn't tell anybody. He keeps it secret in case he needs to sort of defend himself, right? Because solving the cubic equation was one of the big things that they were doing at the time. So then he tells these two students here. Okay, well, what happens then is people start to hear that there is a solution to the cubic equation. And eventually, another mathematician comes on the scene, and his name is Tartaglia, I'm gonna guess. I don't know, it's one of those Italian GL things that I don't know what to do. And now he was alive, let's see, from 1499 to 1557. So again, also sort of in the first half of the 16th century. I think I said these were alive in the first half of the 15th century. I meant the first half of the 16th century. That is to say, the first half of the 1500s. So all three of these people were alive in the first half of the 1500s. So what happens now is Fiore challenges Tartaglia to a mathematical battle, because he thinks that he can beat him simply based on the fact that he knows all of this cubic stuff, all of this depressed cubic equation stuff. But he actually knows a lot more than he does, and so he wins the challenge. Now here it appears that the challenge wasn't a university position, it was just the honor of being the best mathematician around or something. And also apparently the loser had to throw the winner 30 different banquets. Well, graciously, Tartaglia said, I'm not going to do that. I just want the honor of winning the competition. Now, an interesting thing that happens. Well, let me erase some of these names. At the time that this is going on, there's another mathematician named Cardano, Girolamo Cardano. That was Tartaglia. Let's see. There's another mathematician. Okay. Gotta change the slide here. Cardano. Now, Cardano is alive from, he makes it a little bit more into the 16th century, 1501 to 1576. So he hears about this mathematical battle going on. He is teaching mathematics publicly to poor youths who want to know about mathematics. So he's teaching mathematics to them. He hears about this mathematical competition going on. He hears their solution to the cubic equation, and he wants to know what it is because he wants to write a book that includes the solution to the cubic equation. Well, what he does is he contacts our friend from before, the winner of the contest, Tartaglia. Tartaglia. I am now I'm just substituting a character from The Godfather instead of saying his name correctly, so my apologies. Anyways, he contacts him and says, so Cardano contacts him and says, you've got to come to me and tell me what the solution to this equation is. He's like, no, I've got to keep some of this stuff secret because I also want to be able to protect my job if I need it. Well, eventually they get together, and Cardano is able to get the information, and Tartaglia doesn't just give the information, he writes a poem about it, which to me is a very interesting way of doing mathematics. I think it's a beautiful way of doing mathematics, but perhaps not the most efficient way at doing that. I'm not necessarily knocking that as something to do, but to me it's just so different than how we do things nowadays. This is sort of really taking the sort of written rhetorical version of mathematics to an extreme. So anyways, Cardano promises that he is not going to publish his results, Tartaglia's solution to the cubic equation. He publishes a book called Ars Magna, that is the great art, and he doesn't. He is true to his word, and he doesn't put the solution. Well, what happens is, as time goes on, Cardano really wants to put the solution to the cubic equation. He doesn't want to break his oath, but Tartaglia is also not really budging any. So what Cardano does then is he goes back to the students, Fiore and Delanave, of Del Ferro. Remember, Del Ferro was the one who was the first one, perhaps, to solve the cubic equation. He told his students, Fiore and Delanave. So Cardano goes back to those two guys and is like, can I look through the papers of your teacher? They say yes, and what happens is Cardano finds the solution in Del Ferro's papers. Well, now he's got the solution not from Tartaglia, but from a different mathematician who's dead now, and so he feels completely justified in publishing it. And he publishes it in this book right here, the Ars Magna. I'm not going to read the rest of it, but it just means the great art or the rules of algebra. Okay. The great art, subtitle, or the rules of algebra. And he publishes the equation here. So I want to talk a little bit about what's called Cardano's formula, but it's really not Cardano's formula. It's Del Ferro's formula, or Tartaglia's formula, or somebody else's, but it's definitely not Cardano's formula. He's just the one that publishes it. And so it's just, again, it's interesting that in their desire to hold on to their mathematical results, what happens is that other people hundreds of years later, half a millennium and more, or I guess, half a millennium half a millennium later, are now they're not getting credit for it. Somebody else is getting credit for it. Anyway, so here's what he has. Here's what he does for his formula. And again, this is to solve the depressed cubic equation. And in this form that we're going to look at, the solution is going to be x cubed plus px is equal to q. So what happens is that you break this into a system. You convert this into a system of two nonlinear equations that are easier to solve. So again, you're going to take this equation here, this sort of depressed version of the depressed cubic equation, x cubed plus px is equal to q. And again, p and q are positive here. And what you're going to do is you're going to break it into, you're going to break it into a formula. Sorry, you're going to break it. You're going to sort of find two nonlinear equations that you can solve that's going to lead to a solution. So in particular, as I say, you're going to find u and v such that u cubed minus v cubed is equal to 3, and then u cubed v cubed is equal to p over 3 cubed. The reason that this helps is because it had been known a long time. This is one of the things in the book that we covered before. If you to find two numbers such that you know the difference of their cubes and you know what the product of their cubes is, then you can find the two numbers are. You know what u and v are. So again, this system of equations, u cubed minus v cubed is equal to q, and u cubed times v cubed is equal to p over 3 cubed. It was known how to solve that type of equation already. Okay, so that being able to reduce things to that is great because we know how to solve that type of equation. Okay, so then I have the solutions here, u cubed and v cubed. That's what u and v are. So to figure out what they are, you take a cube root, and then v cubed is equal to what I have here, and then x is equal to u minus v. The x equals u minus v is a solution. And so in fact, to verify that u and v defined this way are solutions, just take x, which is equal to u minus v, and plug it into this equation. So let's see, which equation? I have the right formula here. Yeah, okay. So take x equals u minus v and plug it into this equation here. So you're going to get u minus v cubed plus p times u minus v. And then if you do a whole bunch of algebra, you'll get that, it comes out to being equal to q. So in other words, x defined this way as u minus v. X defined this way here. Notice this is just u minus v. If you look at the values of u and v here, this is equal to u minus v. That is the formula. Okay, now he also solves x cubed equals px plus q. Now, what happens for this solution? The only difference for this solution is that the pluses, if you look here for the definition for u cubed and v cubed, the pluses in the square roots become minuses now. The pluses become minuses. Well, as soon as the pluses can become minuses, you get a problem that there could be complex roots. So in fact, that's what we have the next slide here. I probably should have arranged things a little bit better. So q squared over 2 plus p cubed over 3, that's relating to the formula that we have here, okay? But notice p and q can never be 0. Q and p can never be negative. So q and p are always positive. So q squared over 2 plus p cubed over 3 are always going to be positive. So this can't quite happen. That first item can't happen. But what can happen is that second quantity could be less than 0. And that's the exact quantity that you would have in a case like this, where you've got x is equal, where you've got u and v defined this way. So in other words, in this case right here, in this case right here, if you look at this equation here, the difference in solutions is that there's going to be minus signs there. Okay, so in other words, what happens is that you have the possibility of having a negative number, okay, in the square root sign. Now, if you think about x cubed plus px, if x cubed plus px equals q, if you want to solve that equation and you assume that p is positive, for that there's always going to be one real root. Okay, but you don't have that. There's always going to be one positive real root. It's a cubic equation, so there's always going to be a real root. So one of the things that Cardano says when he kind of is like, well, I end up with taking the square root of a negative number, and what's that supposed to mean? He says, so progresses arithmetic subtlety, the end of which, as is said, is as refined as it is useless. So in other words, what he's saying is like, well, we can push these symbols around, and we can kind of get something that we call a solution, but it doesn't really mean anything, and it's kind of useless because what is this square root of a negative number? Now, he actually said that about solving quartic equations, or maybe quadratic equations even. Not in this case, because in this case we can actually things cancel and we actually do get real numbers. But for the quadratic case, if you have negative number in a square root, you have to use imaginary numbers. So he was like, I can kind of deal with these and move things around and manipulate them, but what does it mean? I mean, what does the square root of minus 5 mean? It's meaningless. It's useless. It's refined in the sense that we're doing all of this sort of fancy sounding stuff, but it really doesn't mean anything in reality. It doesn't really correspond to anything in reality. Remember, these are people who had a hard time accepting negative numbers as solutions to equations, so having imaginary numbers or non-real numbers is something that you can imagine would be quite a bit of a challenge for them to understand conceptually. It's kind of even difficult for us to understand conceptually. Not that we're smarter than them, but we're just, we have the benefit of 500 years of mathematical development. Okay, so the next couple of things I want to say is we have Ferrari, which is a great name for a mathematician. He was a student of Cardano. He solved quartic equations. His method was to take a quartic equation like this, and by adding quadratic and linear terms to both sides, he was able to eliminate the square term. So you just have an equation like this. And the thing that you would have to do, there'd be to determine what you need to add to the left and right hand side to get rid of the square term, you have to do this. There's a parameter called b, and that solves the equation b cubed plus pb is equal to q for some values of p and q that are related to the equation here. So in other words, to take the quartic equation and reduce it to an equation without a cubic term. To take a quartic equation and reduce it to an equation without a cubic term, you have to be able to solve this depressed cubic equation, which of course, as a student of Cardano, he knows how to do. Following that, just kind of briefly going through a few things here. Babeli and complex numbers. So he was the first one that really sort of clarified complex arithmetic, developed the rules for complex arithmetic. Now his development of the rules were kind of really an analogy with the rules that we already knew. He didn't really prove them as such because he didn't really have a solid idea of what he was dealing with. But he did introduce them as numbers that we can lead to real solutions. So again, if you think about equations to cubic or solutions to cubic equations, there's always going to be a solution, even if the square root of this, even if there's an intermediate step where you have a complex number. The end is always going to have at least one real solution. Okay, so we go more and more toward symbolism. This becomes easier to deal with simply because dealing with symbols is easier and more abstract. Sometimes making things more abstract makes things easier to deal with. Once you start dealing more abstractly with things, we're able to solve more equations and just understand things a little bit better. Yes, okay. So key themes of the Renaissance, again, I mentioned this at the beginning, but to sort of close things out, we have commerce and competition that were sort of driving mathematical discoveries. And like I mentioned before, there's a gradual acceptance of new ideas, like complex numbers, or even more, even less ambitious, just a non-Roman numerical system. Okay, so again, this is sort of a transition to modern mathematical reasoning, modern algebraic reasoning. And I'm sure it was an interesting time to be alive and be a mathematician or involved in mathematics, but also a very confusing and challenging time. Just because things that we take for granted, they were still working on developing. So many smart minds going into